PDF that we're going to be working from today. We are going to be spending a little time digging into series and convergence tests. I'm going to be here until about 5 o'clock. This is, I mean, you don't have to be here the entire time if you want to. What I've decided, like sort of designed this time to be, is to do a little bit of like practice. Hopefully you've done the lesson for today already. You don't have to, obviously, yet, but the lesson is a good sort of reminder of a lot of the issues that we're dealing with here. I've tried to narrow it in as much as possible on the topics that are on the test this year. But frankly, and as you've probably seen if you've been watching any of the College Board videos, it is really hard to do that with series. It's kind of like telling somebody, hey, we're going to teach you how to do like divide fractions. It's like saying you're going to tell somebody how to divide fractions and only divide fractions. Well, to be able to do that, you have to also be able to multiply integers and multiply fractions and things like that. So not all of what we're doing today is technically on the exam, but I want you to have those tools in mind because they can be useful tools for actually making problems easier for you if you have other tools in mind. Let me do attendance real quick and then we'll get started. I'm going to ask y'all to come off your microphones at certain times. Certain times I will be doing a little more explaining. So we have Madison, we have Tweevy. Good afternoon, Allison. Good afternoon. Nemit's got a new seal going, which I appreciate. He's very cute. Claire is here. Giselle is here. Clay, Jessica, Steven. Who else did I miss? Did I miss somebody? Somebody call out or like put in the chat if I missed you. All right. Cool. Let's go ahead and get started then. All right. This opening time is something I want us to like you to come off the screen or come off the oh, Nina joined us. And Nina. I do want you to come off the microphone at times when you're contributing, because I do want to make the opening part of this a bit of a discussion, okay? I want to sort of get a gauge for where people are at in terms of their understandings of a few things. So I'm just going to pose the question. What do you remember are important ideas in each of the following topics? I want us to talk about these before we look at some examples. For example, in geometric series, what are some things, and come off the microphone, what are some things that we need to remember that are important about geometric series?
The R?
Yes, we need to keep in mind what this R value thing we often talk about with geometric series is. So let's make a note of that. Geometric series have the form like this. Generally speaking, they look like this, but they can, oh, not to the zero. They can vary a little bit. Where our R value, is what we call like the ooh, I think someone else. We have people popping on and off. Hold on a second. I want to make sure that I got the right attendance. Alvin just joined. Okay. Where R value is what we often call the common ratio. Okay. And want to add any more to that? What about this R value? Why is it important? What do we care about? Why do we care about it? Things like that.
It has to be less than 1.
It converges when R is less than 1. We'll be a little more specific. A geometric series converges when the absolute value of R is less than 1. Geometric series you can always recognize because to go from one term in the series to the next one, you will always multiply by the same thing. If the series I just wrote, we'd multiply by half each time. So our R value would be half, and the absolute value of half is less than 1. Therefore, the series converges. The geometric series will converge. And so this does mean that our R value could be negative. We could have a series that's like 1 minus half plus 1/4 minus 1/8. And in this case, we'd be multiplying by negative half each time. The absolute value of negative half is still less than 1, so the series converges. Great. The other big thing to remember for this one is that the sum of a geometric series is equal to A over 1 minus R, where A is the first term in the sequence. Remember, first is kind of a bit subjective. By first, yes, n could start at 0, but the first term is whatever that the first number it would generate would be. Okay, so for example, the first term over here would be 1, whatever. Same thing with this other series. So A is the first term in the series. Basically, whatever we get by plugging in that first n value. If the n value is 0, we'd plug it in and see what we get. Over 1 minus r, where r is the r value, the common ratio. Okay, we'll definitely do some work with that here. Talk to me about p-series. What are some important concepts or ideas related to p-series that we need to remember?
The p has to be greater than 1.
Okay. Thing we're talking about. Well, in a p-series standard form kind of looks like this. The sum from 1 to infinity of 1 over n to the p. 1 over n to the p. This p is a power. It's a whole number. Some books and stuff will define it as it has to be a number. It has to be a number greater than 0 or greater than or equal to 0. But the rules really definitely apply for like any p value. As an example of this, a p-series could look like this. For example, a p-series where p is, say p is 2, where p is 2 would look like this. 1 over when n is 1, 1 squared is 1, plus 1 over when n is 2, 2 squared. This would be a p-series where p is 2. Then I have 1 over when n is 3, it'd be 3 squared, plus 1 over 4 squared. Notice it's different. It's not the same thing as a geometric series. We're not multiplying by the same number each time. The denominator is changing, but the power of the denominator is the same the whole time. Stephen, what did you say about the value of p? Why do we care about it? What do we look for?
It has to be greater than 1.
So if p, that power, is greater than 1, our p-series converges. If that p value is less than or equal to 1, our series will diverge. And these basic rules sort of undergird a lot of the series work that we will do over the next couple pages, but then also your series work in the future. These two kind of properties in there, we'll do a lot of that work. As a side note, the situation when p is 1 has a special name. Situation p is 1, so 1 over n like this. That gives us the series 1 plus half plus 1/3 plus 1/4. As a special name, it's called the harmonic series. The harmonic series, when p is 1, that sort of forms the boundary between the convergence and divergence series. That harmonic series does diverge. So it should be a dot, dot, dot. It does diverge. All right, let's talk about the alternating series test. Heard a lot from Stephen so far, so I want to hear some other voices. I appreciate the contributions for sure, Stephen. I want to also see if there are other people right now who remember some things. What are some important ideas around the alternating series test? What are some of the conditions that we need to find to make it happen, to use it, things like that? Okay, so it is positive. Great, so let's talk about that. So an alternating series is a series that looks like this. This is kind of our general form we think about for alternating series, where we have -1 to the n times, well, we got a couple ideas we'll pop in here, times some function, some series or sequence value in here. And whatever that value has to be, it has to always be positive. So if this is an alternating series, that's an alternating series. There are kind of 3 things to use alternating series tests that we need to check. One, whatever that a sub n is, the stuff that's not -1 to the n. Think about -1 to the n when n is 0, -1 to the 0 is positive, the -1 to the 1 is negative, -1 squared is positive, -1 cubed is negative. That gives us the alternating part. This other part of the series has to always be positive. Quay also mentioned, I believe over there, that to apply the alternating series test, we also need to make sure that, I often list this as the third thing, that this a sub n thing, a sub n plus 1, so think about this as like some term, but the next term has to be less than a sub n. We kind of think of it as eventually. Eventually, we get to the point where the next term is less than the previous term, which essentially means for us that a sub n has to be decreasing. Right? Think about it. If you have a situation where a sub n, the next term, a sub n plus 1, is less than a sub n, the previous term, well then a sub n is decreasing. And our sort of middle thing we have to check condition-wise is that the limit, as n approaches infinity, as the sequence continues, that a sub n thing has to go to 0. What's kind of nice about this is we have a similar test that sort of roots this, called the nth term test for divergence. You might remember the nth term test for divergence. You might recall if you have the limit of, this is not an alternating series, but in general, the limit of a series, if the limit goes to infinity in general of the individual term, if that is anything that is not 0, then it diverges. But the nth term test basically says, well, if you find the limit of your series sequence terms goes to 0, it's inconclusive. We don't know. So what's great about an alternating series is if the limit does go to 0 and these other things are true, then we do know that it converges. So this is why the alternating series test is actually fairly strong. Okay, this is just a side note. This is not technically on the test, but just trying to make a connection. And if we can check these things and all those things are true, then the series we're looking at will converge. And lastly, the ratio test. This was not on the lesson for today, but I wanted to bring it up. This one I want to kind of just fill in the notes for before we jump into thinking about some practice and some, and having a discussion, because I really do want y'all this to be a time to ask questions when we're looking at practice problems to help you like really understand what's going on. Okay. So the ratio test. The ratio test is one of our convergence tests. It's a convergence test, and what's nice about it is it connects really strongly to this idea of absolute convergence, which I will reiterate is not on the test, but is a highly convenient thing to be able to check, and actually often makes our lives a lot easier. Even though it's not on the test, you're welcome to use absolute convergence to prove things. The ratio test is on the test. So here's the ratio test, right? If we have some series, I'm going to make up some series, right? 0 to infinity. We have some series, then we find the limit as n approaches infinity of a sub n plus 1. So basically we take the series, but instead of n, we say n plus 1, divided by a sub n. Take the absolute value of that, we get a limit. Here's what we know. If L is less than or equal to 1, so if that limit we get is less than or equal to 1, then our series is absolutely convergent. And absolute convergence implies that the series is convergent. The reason why we check absolute convergence, I know we've not actually technically done a lesson on this, still you hear me saying a lot. The reason we check absolute convergence is it's a stronger version of convergence. Basically, we're saying alternating series tests, as we can see, because of this middle thing, actually it's kind of relatively quote unquote easy to converge. Basically, this absolute value bar says, well, let's forget the alternating part. Does our series converge even without alternating things? If it does, we call it absolute convergence. That means that our series converges. It's a strong convergence, we can call it. If that limit that we find, whatever it's comes out to be, is greater than 1, then the series is divergent. And if it equals 1, then we're kind of stuck. I won't even put therefore. It's just inconclusive. It actually doesn't tell us anything. The ratio test is actually a really convenient test. It's relatively easy to use because a lot of stuff cancels out nicely. Those are 4 big series-related topics that are still included on the AB exam. Any questions or things at this point? So it's just kind of set up. I do want this to be a discussion. I do want you to ask questions if you're feeling like.
I have a question.
Yes, go for it.
What's the difference between the alternating series test and the alternating harmonic series test?
There is no such thing technically as the alternating harmonic series test. The alternating harmonic series is the harmonic series, but instead it's 1 minus half plus 1/3 minus 1/4. And you could use the alternating series test to actually show that. Do you all want to do that right now? Yes, Mark Walter. We'll change one of those. Madison is unsure. I'm actually going to change one of these then to make that the case. Let's go ahead and change this one down here. So instead of what I have for 2b, let's do what Stephen is referring to. So the alternating harmonic series looks like this. All right, it is -1 to the n over n. That's the alternating harmonic series. And we want to show whether or not the series is absolutely convergent, conditionally convergent, or divergent. Okay? So here's what we can do. Let's start with the absolute convergence part of this. Okay? Absolute convergence. How do we do that? All we have to do is check whether or not, one way to do it, for example. We can also use the ratio test to do it, but we're not going to do that right now. We'll use what we know about alternating series to do that. The absolute convergence, basically we say, all right, let's take the absolute value of those terms. Let's find this series. What's going to happen to this series? Well, notice the absolute value here, we'll get rid of this -1 to the n because they're not going to care about the sign. So this is really equal to.
So it's a p series?
It's a p series, exactly. This basically kills the alternating part of it, turns into a p series. It's a p series. Notice it's a p series with p being less than or equal to 1 and is therefore divergent. Now pause. We did not actually check our original series. We checked for absolute convergence. So what this thing means, since we found out that the absolute convergence, basically this means that it's not absolute convergent. It is not absolutely convergent. Our original series is not actually absolutely convergent, but we haven't checked the original series. We checked for absolute convergence and found out that the absolute value of it turns out to be a series that diverges, so it's not absolutely convergent. But we could use our alternating series test on this specific guy here now. And remember, the alternating series test says, right, given some series, if we ignore the alternating part, we'd have this sort of a sub n thing. Let's check what's going to go on there. A sub n, let's kind of check our three things. A sub n is 1 over n. From 1 to infinity, is 1 over n always positive? That's our first check. Yeah, it is. So it is greater than 0. All right. What else do we check? We check the limit of that thing. The limit is in approach infinity of 1 over n. Well, what's that limit come to? 0. Great. It needs to pass that check to be able to use the alternating series test to check this. The final check we need to compare is, well, what's going to happen if we compare 1 over n plus 1? So remember, we got to compare a sub n plus 1 and make sure that it's eventually less than a sub n. So our a sub n is 1 over n. So a sub n plus 1 is 1 over n plus 1. I just kind of substitute n plus 1 in for my n value. Is that going to be less than a sub n, which is just 1 over n? Yes, right? Because n plus 1, that'll be a bigger denominator than n. So my a sub n plus 1 is going to be less than 1 over n because the denominator here is bigger, making this fraction smaller. Great. And then you can say, therefore, my series here converges by the alternating series test AST. So this would be an example where our series is not absolutely divergent because we took the absolute value and it turned out to be divergent. So it's not absolutely divergent. So gosh darn, not absolutely convergent, but it is regularly convergent by the alternating series test. Questions or thoughts there? So that proves what Steve was saying about the alternating harmonic series is convergent, but not absolutely. Thoughts, questions? I want y'all to be active. Let me know what I can do for you. Things on your mind. The goal is to come away from this feeling better, right? Feeling that you've learned a little bit, tackle some more problems. I don't particularly care how deep we get into this packet as long as we're feeling better. Okay. Oh, Allison, yes. Are we going to go over other series like the limit, like the limit comparison test and those things? So I will not be this week covering those things. I will offer some other times that if you would like to go back over those things before the test, a chance to do that. Given that those are less useful tools, I've tried to keep all the things that are useful for the test, which does touch things like absolutely convergent and like nth term test. Limit comparison tests, those kinds of things aren't super useful given the problems that you will probably see. So I will have time to go over those, but not this week. Okay. I definitely won't leave y'all hanging for math classes beyond this. You will need those other tests, and so there will be times to go over those things. I won't leave y'all hanging on that. All right. Cool. Let's back up then and do a little more of the sort of practice for things. After each one, I do want some of them I might hand to you to try. Other ones I might just. What about? We won't necessarily, Stephen, get into that a whole bunch per se. Just because it's not like given our timeline and the fact that it's not like a true like a BC calculus kind of hit that we have to do, we won't spend a lot of time with that. But if you want to talk about it, I can. The phi series or phi, depending on how your Greek teacher taught you to say it. All right, let's do this. For what values of x do the following series converge? Now I want to talk about this one. This is technically what we're finding here is what we call the radius of convergence. Notice for 1a here, n is our counting thing. X is just some, I don't know, x is some variable, right? If we solve for some variable that makes a series converge, we call that the radius of convergence. Basically, what is the range of numbers that makes this thing converge? The radius of convergence is not on the test this year, but can be a very convenient tool for solving certain things. And it lets us flex some ideas around like geometric series. So let me give an example here. This works in both geometric series and some thinking work. All right, so let's say we have this series. This looks a little funny, 2 to the n times x to the n. That means this series is really just the same thing as n equals 0 to infinity of, we could call it 2x to the n, right? Okay, 2x to the n. So I go, well, wait a minute. If this series is going to converge, that's what I want. If this series is going to converge, I can really think about it like this. This thing is really, I'm going to do a little arrow that's not really equal to. 2x, that's going to be some number, right? X is something, that's going to be some number. I can call this like Dorito to the n, right? Pause. Come off the microphone and put something in the chat. What do we know that this thing in parentheses needs to be if this series is going to converge? What do we know about what the inside of this parentheses needs to be if we want this series to converge? Any thoughts? Whatever this number is, less than 1. Whatever this number is, this Dorito thing, what does it need to be that will make this series converge? Any other thoughts? Yeah, that's what I'm thinking too. Let's just assume, because we know that geometric series kind of look like this, and we know that geometric series need to have an absolute value of r less than 1. So really, if we want to, we can really think about that Dorito thing as for our geometric series. Ooh, that got a weird looking sigma. That's really kind of like r to the n, and we know that the absolute value of r needs to be less than 1, right? So let's go back to where we kind of started over here. This is really our series. We just figured out that this inside part, if this thing's going to converge, the absolute value, this is going to be our R value. Our A thing out here is just 1. Our R value is 2x. The absolute value of 2x has to be less than 1. Well, what does that mean? Well, that means if I give her this absolute value, that 2x has to be, not just x, 2x. 2x has to be between -1 and 1, right? An absolute value really gets rid of the negative sign, so I can split absolute value inequalities like this. So what does that mean x has to be? This leads us to the conclusion if I divide everything by 2, that x has to be between -½ and ½ That's what we call the radius of convergence now. We now know that the radius of convergence is ½ basically plus or minus ½ Again, that is not a skill that's on the test this year, but this is a good tool for sort of thinking about geometric series, because even if they don't ask about radius of convergence, even if they don't use that phrase, they could ask, if this is a geometric series, what values of x will make this converge? That is a geometric series question. Thoughts or questions about this process?
Mark Watcher, can I ask a really quick question?
Yeah, this is your time. Do it.
So you said 2x is r, right?
Yeah, because 2x, x is some number. 2 times x is going to give us some number. And so I'm just going to think about this as my r, whatever that ratio number is, I'm going to multiply by each time.
Why isn't 2a? Like, you know how it's ar to the nth power?
Yeah, because in my very original series, that 2 was part of the n thing. And remember in our general summation for geometric series, that r value is the stuff with the n.
Right. Okay.
A is just some constant factor there. Because it's 2 to the n, that n is attached to that 2 as a
okay.
It's going to be part of the r.
Right, okay. I got
Yeah.
it. Thanks.
Yeah. All right. Hey, give it a shot. Take a look at this next one. See if you can go through a similar process. See if you can think through this next one. For what values of x do you think here that this next series is going to converge? Give it a shot. I'm going to work on it myself too, and then we can talk about it. All right. So this is how I would approach this one. Again, we have a similar situation. It's alternating, but we know for geometric series, it doesn't particularly matter if it's alternating. If we can force something to be a geometric series, great. Geometric series are super easy because they follow these really basic patterns of what is R, what is A. So I've kind of forced my -1 in here and said, oh, great, we have blah to the n. Here's my R, so the absolute value of R has to be less than 1. Well, the absolute value of negative, that'll go away. Broke it into my 2 inequalities, my compound inequality here. Subtracted 1 from everything, and just found out my interval of convergence, my radius of convergence. Turns out my radius of convergence is still 1. The radius of convergence is 1 still, if they had asked me that, but they're not going to, remember. The radius of convergence is 1 because you kind of go plus or minus 1, right? The difference between negative. Basically, x is centered at -1, and you go down 1 from there or up. Thoughts or questions looking at these problems? I've asked some good questions. Please do keep it up. Again, want this to be you coming away feeling a little better, a little more secure. Yeah, so basically, Mastin, if we want to, we can actually just take the average here, basically find out, I mean, imagine a number line that are basically what we just said is our x value. Our x value can range from -2 to 0. So we can ask ourselves basically, where is x centered? What is the center of x? If x can be between -2 and 0, well, what's the halfway point between -2 and 0? It's -1. So if we imagine that's like our center, well, what's the radius on either side of it? 1 to go up to 0 and 1 to go down there. So we say the radius of convergence is 1. You kind of go plus or minus 1 on either side from that center. That makes sense? Yes, so you could also use the alternating series test to do some of this work, but you will eventually actually come down to the same question, right? Basically, the alternating series, you would just end up ignoring the -1 to the n, and you'd be left with x plus 1 to the n, and would eventually kind of have to ask yourself the same questions about what makes it converge. My recommendation is, when possible, jump, if you're talking about like what will make something converge, your geometric series, forcing it into the geometric series pattern is the easiest thing to do. Cool. What have we done? If you want to do 2A, we've already done kind of one like it because we did the alternating harmonic series like Stephen wanted to. I want to point out one other thing, and then let's look at some other kinds of practice and things. 3A. For what values of x does the following series converge? This is the, oh, I didn't even write the whole thing. Did I even write the right question here? I put my right problems. Make sure I even put the right. Let me even make sure I put the right question that I wanted to ask. Oh, no, I did. Okay. All right. Now notice this is a little different, okay? These ones up here, our n values, were in the exponent. That led me to think, oh, this sounds geometric, right? Because geometric is a r to the n. These look geometric to me. Notice in 3a, though, it looks a little different. We have an n that's not in the exponent anymore. We have one that is, but this other n is not. So that means we can't use our geometric series stuff. Remember, geometric series, I can label this for a second. This is not a geometric series anymore. That means I can't use my easy geometric series stuff. I'm going to need a different way to do this. An easy way to also determine the radius of convergence, though, is the ratio test, right? So if it's not geometric, another easy way to determine whether or not a series converge and what that radius is the ratio test. Okay. Now let me give an example of this one. And I actually would like you to try some stuff. So ratio test. Let's go back to, remember, keep in mind x is some constant value. Okay. How does the ratio test work? Well, the ratio test says this. If I take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, and find the limit, then I can tell something about this series and its convergence. So let's do that for this specific problem. The limit, that became a big arrow sign, the limit as n approaches infinity of the absolute value of, okay, so I look at my series. Remember this inside stuff here, that's a sub n. I can go ahead and put that in the denominator, n 3x minus 5, the n. Slap that down there. Now in the numerator of this ratio, like we're making a ratio, a fraction, I need to find all my n's and replace them with n plus 1. Because n plus 1, a sub n plus 1 goes in the numerator. Okay. So this is the limit I need to figure out. Okay, let's just start doing our sort of ratio test stuff. We set this up. Then the good thing about the ratio test is oftentimes a lot of stuff starts canceling out. Here's what I noticed. 3x minus 5. Don't get overwhelmed with the 3x minus 5. 3x minus 5x is some number, so 3x minus 5 is some number, right? If it helps, put a Dorito in there or something, all right? So we have some number to the n, some number to the n plus 1. So essentially what happens here is 3x minus 5 to the n divided by 3x minus 5 to the n will cancel out. What does that leave us? This will leave us as the limit as n approaches infinity of the absolute value of, notice n plus 1 can't cancel out with n. Those are not the same values. Those are going to have to hang out. N plus 1 over n will hang out there. 3x minus 5 to the n canceled out with 3x minus 5 to the n. But there's a plus 1, so there's an extra 3x minus 5 up there in the numerator, like that. Now we can ask ourselves, great, we canceled out everything we can. Now what's going to happen then as n goes to infinity, right? Keep in mind 3x minus 5 is just some number, right? It's just some number. So as n goes to infinity, this number doesn't really matter. So if we want to, we can actually, I'm just going to blot it out for now. Let's ask ourselves, as n goes to infinity, what happens to n plus 1 over n? Go ahead and type into the chat box, what's going to happen as n goes to infinity? What's the limit as n goes to infinity of n plus 1 over n? What is the limit as n goes to infinity of n plus 1? Back to your limit stuff. Ignoring my 3x minus 5, what is the limit as n goes to infinity of n plus 1 over n? I'm going to take just the limit. Okay. People are thinking 1. We're just taking the limit plus 1 over n. Okay, cool. Got a lot of 1s in there. Basically, we just zoom in and focus on the n's. Think about it. Our n behavior model is n over n. As n gets bigger, this plus 1 doesn't matter. So n over n, that goes to 1. Basically, we end up with infinity over infinity, so it goes to 1, right? If you need help reviewing limit stuff, let me know. But yeah, this n plus 1 over n part, it just goes to 1. So, back it up. Let me unblock my 3x minus 5 thing. We just found out that the n part, because n goes to infinity, that's going to go to 1. So what gets left over? Well, we did all the n stuff. What is left over is just the absolute value of 3x minus 5, right? The limit I can get rid of because I took care of all my n stuff. It's the limit of n, so I took care of all of it. All that's left is the absolute value of 3x minus 5. So the limit was 1. Now, this is the result of my ratio test. What do I do with this? Well, we know for the ratio test, right? We want the series to converge. If the series is going to converge, we know that the limit we just found, has to be less than 1. Oh my God, look, this is a lot like the scenario we just had up there with the geometric series. Great. We can deal with that. This means that -1 is going to be less than 3x minus 5. It's less than 1 because I can split my absolute value into negative, positive, negative. I can add 5 to both sides. So that gives me 4 is less than 3x is less than 6. I can divide everything by 3. That'll give me 4/3 is less than x is less than 2. Great. So there are the values of x that will make this thing converge. Technically, this shows us the radius of convergence. One thing I am going to say that we have not learned yet, but will not be able to test is technically, remember the ratio test, we don't know what happens if the limit is 1. So basically, we would have to check what happens when x equals 4/3 and 2. If we wanted to figure out what values of x work, we'd actually have to go back and plug in 4/3 and 2 and check that stuff. Don't get too lost in that. That's not on the test. That's not something that you need to worry about. We'll cover that after the test. Basically, we have to check the endpoints. So mathematically, I just want to cover my butt and say that we've not actually checked those endpoints. But for what you need to know for the test, that is good. Thoughts or questions about that process? Cool. When is it convenient to use the ratio test to solve for convergence? So we found out that this one is not geometric. The ratio test is convenient almost spelled ration. The ratio test is convenient in the following kinds of series. Series that look like this, when we have powers, when all your options don't work and you're about to cry. I actually really like the ratio test because it ends up canceling out things really nicely. So if we have situations with powers, with factorials, they're really useful. I just lost chat name. With powers, they're really useful. With factorials, they're really useful. Situations like that is what we want to be on the lookout for. And combinations of those things. So series that are like k is some constant, k to the n over n factorial times like e to the n, those kinds of situations. Factorials, exponents mixed together, convenient. All right. I want you to try this process then for B. See if you can do the same thing for B. Go through the ratio test. Go through the ratio test. And see if you can figure out for what values of x will make this converge. Again, we're kind of cheating because we're not really checking the endpoints. But please go through this exercise. I'll work it out silently so you can check your work against mine if you are still feeling nervous. I guess technically the radius of convergence for this one above, we would have to do 2 plus 4/3 divided by 2. Figure out the middle spot and then figure out the plus or minus. But we won't worry about that because they won't ask for the radius of convergence. It's not on the test this year. All right. I'll work through this myself too. Already started off wrong. Notice our initial sequence this time is a fraction, so you end up with a fraction over a fraction. We're dividing by a fraction, same thing as multiplying it by its reciprocal. So if you want to check your work against mine, the setup is a little bigger. We have to have a fraction over some other fraction. Remember the n plus 1, basically going in and placing all n's with n plus 1 goes to the top divided by just a sub at the bottom. Dividing by a fraction, same thing as multiplying by its reciprocal. So I flipped my denominator over here to be 5 to the n over n minus x minus 1 to the n. A bunch of things cancel out. I did red. 5 to the n cancels out with 5 to the n, but it leaves me 5 to the 1 in the denominator. X minus 1 to the n cancels out with x minus 1 to the n, but leaves an x minus 1 to the first power in the numerator. My n and my n plus 1 don't cancel. So I carried all that stuff down here. I had 5 to the first power still in the denominator, n plus 1 in the numerator. X minus 1 to the first power still in the numerator, and my n still in my denominator. As n goes to infinity, n plus 1 over n plus 1. It's the only stuff with n's, n plus 1 over n plus over n, sorry. As n goes to infinity, n has the same power, the same strength, so this will cancel out, leaving us with than 1, negative 1 is less than x minus 1 over 5, it's less than 1. Multiply everything by 5. Now space, add 1 to everything, so negative 4 is less than x. It's less than 6. Thoughts, questions, concerns, prayers? Keep in mind for, if this was just, if x was just a, I may, if we want to, we can test this because x should work when x is 0, for example, or x is 2. You can plug it in, do the ratio test, and prove that it converges. If x is 2, we have 2 minus 1 to the n power, 1 to the n power. You get rid of that and check that using the ratio test, and it would converge. Questions? Before we jump and take a look at some sample free response questions, can you just go ahead, be honest with this? It's not meant to be pressure. It does help me sort of gauge, especially when we're all being kind of quiet. You go ahead and type into the chat box all the stuff that we looked at today on a 1 to 5, 1 being totally lost, 5 being super sweet, got it. Let me know where you're at right now. How are you feeling? Threes, fours. That sounds about right. 4.25. Okay, I did not specify if they had to be integer values. I guess that's fair. Okay, 2.5. Okay, now we're doing decimals. Someone's gonna give me that they're pi. Oh boy. Okay. All right. So we're gonna do a little more practice. My goal as your teacher over the next couple of weeks, knowing that some of the BC stuff is the more challenging stuff, is to provide many of these opportunities for us to kind of come together and just keep practicing. So I will by the end of this week also post some upcoming things as well that you can come in and work with me on BC specific skills that we definitely need to just keep shaking the rust on. This test is an ABBC test, so it's not all BC stuff. Keep that in mind. We just got to be ready for it and continue to hone our skills to get better and better and better. Let's do this. I included a lot of different practice problems that I whipped from College Board stuff that they've actually given me. And so this is what I want us to do. All right. I would like everyone to go to the next page. You will need another piece of paper to work on for this one. I want you to look through, consider the series that's given here. Give us a whole bunch of stuff. For p equals 3, x equals 8, does the series converge? Absolutely. Converge conditionally or diverge? Now, the great thing about the ratio test is all that stuff we were just doing, as you might be able to tell, is actually checking absolute convergence. Right? We just checked absolute convergence because we're taking the absolute value of things. What I would like you to do is do part A. For p equals 3 and x equals 8, does this series above converge, absolutely, converge conditionally, or diverge? this one right here. And going to Claire's question, this is one that the ratio test is going to be useful for. The ratio test could be very useful for this if you wanted to use it. Okay. Let's take 2 minutes. Go ahead and do part A. If you're stuck, come on the microphone and just tell me, like, Mark Walter, I have no idea what I'm doing. I want this to be time for questions. You don't have to be released to do this on your own now. But take 2-3 minutes. See if you can do part A. Or jump on and let me know what you need from me. Pull up my answer. Ratio test could be useful here. You don't have to use the ratio test. We also looked at P-series tests. Plug in your stuff and kind of see where it goes, okay? I'm not saying you have to use what I've set out. Take back. Ratio test might not even be the best way to do this. Don't think about it. Figure out what my work was. We are checking absolute convergence here. So plug in your P and your X, see what it works down to. If you get done, try B. Plug in your P and your X, see what it works down to if you recognize what's going on here. Here's what I'd like you to do. In the chat box, can you type in abs con, like cons abs for convergence absolutely, con condish or cond or something like that for condition, or just say did not finish. Where are you at right now? You've been able to figure out from part A. Absolutely convergent, conditionally convergent, divergent, still working. All right, then let's keep going. Keep working for a little bit. I want to apologize that maybe actually when I was thinking about it, my comment about the ratio test could have been a little misleading. It's not necessarily the quickest way to do this one. Be sure you've plugged in P equals 3 and X equals 8 and see what happens. Yeah, I'm with Steven. My comment at the start is very misleading. It's not that you can't do it that way. It's just not the quickest way for sure. All right, go ahead and give me another check-in. Absolutely convergent, conditionally convergent, divergent, did not finish. Still says absolutely convergent. Let me know, absolutely convergent, conditionally convergent, divergent, still working. Let me pause us there then and make a big apology. I'm sorry that I said ratio test. That's not a great way for me to have introduced that, and I'm very sorry. Let's plug in P equals 3 and X equals 8 first, and then sort of reframe. If P is 3 and X is 8, if P is 3 and X is 8, okay, Nina says conditionally convergent. If P is 3 and X is 8, we end up with a series that looks like this, right? -1 to the n plus 1. X is 8, so that gives me 5 to the n over 5 to the n to the 3. Now notice, 5 to the n, 5 to the n, we can get rid of that. Our series becomes this, right? Our series becomes this. Ratio test actually becomes hard to do with that because, I'm sorry I said that. But this does look like something that we have seen before. This series now, what does it remind you of? Type into the box. What does this series remind you of? Instead of P series, alternating P series. Other thoughts? Yeah. This looks like a P series. Remember, if we want to check absolute convergence, we could, if we wanted to, simply say, right, let's take that series, take the absolute value of it, the value of that series, we kill the negative part of this. So we get 1 over n cubed. 1 over n cubed, that converges because it's a P series with P is greater than 1. And then therefore, our original series equals 1 to infinity of -1 to the n plus 1 over n cubed is absolutely convergent. So this is a situation, actually, I'm very sorry, that the ratio test was not particularly useful. In fact, just taking the absolute value and recognizing it as a P series that converges would prove that this is absolutely convergent. Questions or things? It's about 5 o'clock. You're welcome to go if you want to. It's always optional, anyways. I am actually going to stick around to about 5:15. We'll keep working on problems with the people who want it. I am very sorry that I misled you on that one. That's a horrible guidance on my part. I'm very sorry. If you are sticking around, please go ahead and start on part B. Think about the different series that we've done and see what you can do with part B. If you are leaving, just let me know, say goodbye. Do make sure tomorrow I will release the second FRQ practice in Bikeway. I will release the second FRQ practice exam tomorrow for people to do. You get started on, but you have to do it. You're welcome, bye. You will need to get started on, but it's due by Friday. Bye, Tweeby. The physics crew. Looks like some people did stick around. Yeah, P series also. So here's the thing. What the ratio test automatically checks. So the ratio test, if you put that absolute value, automatically checks for absolute convergence. You can always also separately, technically the official way to check for absolute convergence is simply by taking the series, the absolute value of it. That is technically how you do it, which is why you can always just make your series, take the absolute value of it, and check what it does, which is what we did here. I just made my series by plugging in P and X. I said, hey, well, what does the absolute value thing do? I took the absolute value, found out it was a P series that converged, Therefore, it's absolutely convergent. That's technically how you check it. But the ratio test also checks it as well in a sort of like subcategory of ways. Does that like a subcategory of series? Does that make sense? So when is it conditionally? It is conditionally convergent. It is conditionally convergent if, for example, you find that the series is, so let's say I had done the absolute value thing here, and I had found that the absolute value of it is divergent, but then did a different test and found that the original thing is convergent, but the absolute value part of it is divergent, that would be when it is conditionally convergent. So yes, basically you check with a second test. In fact, that's what happens in part B. In part B, for those of you who are here working on it, I can walk through that real quick. In part B, when you do your series here, when you plug in your P and your X value, what you would find is that your series you're looking at, -1 to the n plus 1, that'd be 5 to the n over 5 to the n to the first power. 5 to the n's would cancel out. We'd have the series n equals 1 to infinity of -1, the n plus 1 over n. If I did the absolute value stuff on that, if I check absolute convergence right away, I run into a problem because checking absolute convergence, I would get rid of the negative sign. I basically find that this series is a P series with a P value 1 is the harmonic series. A harmonic series diverges. So it's not conditionally. Our series then is not, back up. Our series is not absolutely convergent. The series is not absolutely convergent. So then what do? We found out it's not absolutely convergent, but what about this original series? Is the original series convergent? If it is, we call it conditionally convergent. So this series then I could check. Turns out the alternating series test does it. A sub n is 1 over n. That's greater than 0. The limit as n approaches infinity of 1 over n is 0. And a sub n plus 1 is less than a sub n because, I'm running out of room here. 1 over n plus 1 is less than or equal to 1 over n. Therefore, by the alternating series test, this series is convergent. It's not absolutely convergent, so we say it's conditionally convergent. Does that make sense, Madison? So if it fails the first test but passes the second test, it's conditionally convergent. We say that the condition was that it was alternating. It only converged because it was alternating. You don't have to explain that, but that's why we call it conditionally. No, it applies to anything. It's just most frequently and most obviously comes up in alternating series. Yeah, we are starting to get where math gets like truly weird and difficult to process because you can't really visualize stuff very well. So the absolute convergent stuff, though, think about it. Because we're talking about absolute values, the absolute convergent stuff only matters if we're dealing with negative signs, really. And so almost always this applies to alternating series. It's not a hard and fast rule, but at this level, yes, you can kind of think about it as like alternating series are the ones that might be conditionally convergent. You can think about it that way for now. So if it doesn't converge, I'll go, Madison's question is easier to answer. If you're checking for absolute convergence and it fails the absolute convergence one, you do have to check another one. However, if you had jumped straight to some normal test, like if you had jumped straight to the like alternating series test and found out it failed, then you can kind of stop. You have to have some test that would show that it's divergent. If you can prove that it's convergent, absolutely, then you're just done. If you can prove that it's convergent with the alternating series test, you're just done, depending on what level of convergence you want to test. If you find that the test is divergent, then you're done. You've shown that the series is divergent, unless you're checking absolute convergence, in which case you still have to check conditional convergence. This is where things get weird. One of these times I'll make a flow chart for y'all. Claire, why do you use the alternating series test if you already found it's a harmonic series and it is divergent? We didn't actually find that the series is divergent. The actual, remember, is this one, the one I'm boxing in red. This is the actual series that we're checking about convergence and stuff. The thing down here, where I found out it was a harmonic series and diverges, that is the absolute value, not the actual series we're checking. We found that the absolute value of the terms series is divergent. But that's not actually the series we were checking. We checked down here, this check we first did determines absolute convergence. If you find that the absolute value of the series of the absolute value is divergent, it doesn't actually show you whether or not the series you're looking at is divergent or convergent. Okay. Correct, because they are now different things, right? They are now different series. Our original series had an alternating negative sign. So taking these things are not equivalent. This part up here inside my series and this part are not actually the same thing, right? Okay. Mass, the time gets busy because I have a conference with the AP or the College Board people. But yes. Why? Why do we take the absolute value at all? Because we, in this question, were looking to determine whether or not the series was absolutely convergent. Basically saying, and if we need to, I'll back up a second here. Basically saying, does our series converge without, if we ignore the alternating part of this? And here's, maybe this is, I want to take a big digression if everyone's okay with that, because I think this will be better for your overall math understanding. So bear with me here for a second. Big digression into series, because I'd rather you like really understand series stuff than just like taking the AP test to pass it. Okay. Let's do this. I'm going to graph out a quick sketch. Our most obvious example of this is comparing the harmonic series. 1 plus half plus 1/3 plus 1/4 plus, and so on and so forth. We're going to compare it to the alternating harmonic series. -1 to the n or -1 to the n plus 1, whatever you want that to be, over n, which looks like this. In this case, it would be -1 plus half minus 1/3 plus 1/4 minus 1/5 plus, and so on and so forth. Let's actually compare the graphs of each of these things. And this hopefully will indicate for you why we do care about the difference here. Now, if this is our n-axis, and this is the value, we can call this like 1 over n. When n is 1, our first term was 1. When n was 2, our term was half. When n was 3, it was 1/3. When n was 4, 1/4. And we get a series, if we plotted the actual sequence, that looks something like this, right? It's decreasing over time, or over as n increases. Now think about what we call these the partial sums. Ignore the half, 1/3, 1/4. If I stopped at 1, my sum would be 1. If I stopped at my second term, my sum would be half. Sorry, 1.5. If I stopped at my third sum, I would have 1.5 plus 1/3, so that'd be 1.83 repeating. right? And then if I stopped at then I add 1/4 to it, my partial sum, my fourth partial sum would be I gotta add 1/4, so I gotta add 0.25 to this. 0.25, if I add that, actually will take me 2 point, if I add 2, that would give me 8, that's not right, 2.083 repeating. Notice as I add terms here, it keeps getting bigger, and we could prove that it actually gets bigger too fast, and so there's never a limit. It diverges. The sum as we increase here, the sum of the series just keeps on increasing to infinity. Slowly, 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 but it does. Now let's compare what happens to the alternating series test. It is related to finding improper integrals. You can actually use improper integrals to prove that something converges or diverges, called the integral test. So it is related, yes. The alternating harmonic series here, let's plot its points. When n was 1, our first value in our series was -1. And then when n was 2, we had a value of +0.5. When n was 3, we now have a value down here that's like -1/3. When n is 4, we have a value of like 1/4. When n is 5, we have a value of -1/5. So notice if we kind of measure our point bounces back and forth, positive and negative. Now think about what that means though. Think about what that means for the sum. Think about what that means for the sum of this series. For the partial sums, my first partial sum, if I just add the first term, is -1. If I add my next partial sum, -1 plus half, that'll give me -half as my sum. And I subtract 1/3, that'll give me negative, my third sum would be -0.83 repeating. My fourth partial sum, I would add 1/4 back to that. That'll take me to -0. Whatever that ends up being. -0.5 something, and so on and so forth. Notice, look, think about the difference here. This sum, as I add to it, bigger, bigger, bigger. This sum keeps bouncing around. It was -1, then it was -0.5, then it was -8.3, then it was -0.5, then it would be -0.7, there'll be -5. So it bounces back and forth. And because of that alternate, we have plus. So we take some away, then we add some. We take some away, then we add some. Take some away, we keep doing that. And so it kind of cuts itself off. It kind of chops itself. We add something, we lose some. We add something, we lose some. We add something, we lose some, right? We keep getting closer and closer because we add some, but then we take some away. Add some, take some away. So it actually gets closer and closer to some value as we continue down the road here. It is going to approach some limit and it will converge. Why am I saying all this stuff? Because this is the difference between being absolutely convergent and conditionally convergent. This series, if I ignored the -1 thing, I would have the harmonic series. If I ignore the alternating part of this, my series would actually diverge, as we showed. But because it is alternating, and we get this minus, plus, minus, plus, minus, plus, because it is alternating, it converges. So we say it is we say that this series then really only converges because it's alternating. But it's nice to know whether or not a series would converge on its own without it alternating. And so if I just say, okay, well then, let me check to see if it is absolutely convergent. In other words, on its own, would this series converge without the alternating part? The answer is no for the alternating harmonic series because you'd end up with 1/n. And we know that this series diverges. This series diverges. So my alternating harmonic series, yes, it converges, but it converges conditionally. The condition is it only converges because it is alternating. Its like natural counterpart is divergent. So we say that this series is conditionally convergent. It's convergent on the condition that it is alternating, which it is. So taking the absolute value of it is not checking the same thing. We're basically checking its positive counterpart and figuring out, hey, would this series I'm looking at that is alternating, would it converge or diverge without the negative sign? And if it diverges without the negative sign, we say, hey, then this guy is actually conditionally convergent. It only converges because it has the alternating part. But some series, for example, the series that would be alternating -1 over like n squared, we do a similar graph. We go minus, plus, minus, plus, minus, plus, minus, plus, minus, plus. It is alternating and converges. We could think that it converges. If we took the absolute value of this and checked for absolute convergence, we get 1 over n squared. And look, if we kind of remove the condition of the alternating, look, it actually converges without the alternating part. It would converge anyways, right? It would converge anyways because this is a p series with p is greater than 1. So basically we'd say this is absolutely convergent. Again, if I now get rid of my things. My original series that I was checking, which was the alternating thing. This series that I was checking is absolutely convergent because when I take the absolute value of the terms and do its series, it would converge even without the alternating part. So my original series is absolutely convergent because it would converge even if you took its absolute value. Long explanation. Does that help? Yes. Now here's the difficulty. Let's say that you were just given some series. I just like handed you one. Some another. If I just went straight to the alternating series test, and said, okay, well, a sub n is 1 over n to the 7/3. Sorry, that's greater than 0. The limit as n approaches infinity of 1 over n to the 7/3 goes to 0, and a sub n plus 1 is less than or equal to a sub n. If I did all my alternating series stuff, this does not actually prove absolute convergence, though. All I did was prove that it's convergent. All I did was prove that it's convergent by the alternating series test. So I actually didn't check its absolute convergence. To check absolute convergence, we would do what we just talked about. We would actually need to take the absolute value of it and check to make sure it would converge even without it, which is kind of an easy thing to check for this specific thing. Up here, that would give us the series 1 over n to the 7/3, which is a p series, p greater than 1. And so it does converge absolutely. But this stuff down here does not actually check absolute convergence. Does that help? I don't like giving hard and fast rules. At this point in math, we got to stop thinking those hard and fast rules, like whenever we see a blank. As you get more comfortable with it, you'll start being able to tell when certain tools are going to be more useful. For example, I can actually give a series that that is alternating, that is not super convenient to do the alternating series test with, right? I could give you a series. I could give you a series here, for example, like -1 to the n times e to the n plus 1 over n factorial times 5 to the n. This becomes a lot more challenging to do the alternating series test with, but was actually be really convenient for the ratio test. So just because you see a -1 to the n doesn't necessarily mean that the alternating series test is the easiest way to do it. Could you use the alternating series test? You could try, yeah. You might have some hard numbers to work with, but it would quote unquote work. It's not necessarily the easiest tool in the toolbox. Additionally, I can make up a series that looks alternating, but is not. This series looks like it would alternate, but it actually is not going to be alternating. This series does not alternate. How do I know that? Because as n ticks up, sorry, it should be an n. -1 to the n, that will alternate, but what about sine? As I plug in things, sine of 1, well, that would be positive. Sine of 2, sine of 2, that would be positive. Sine of 3, that will be positive. Sine of 4, uh-oh, I end up with a negative sign. Remember for the alternating series test, for it to be an alternating series thing, then a sub n always has to be greater than 0. So this looks like it's an alternating series, but it's really not. Just because you see the -1 doesn't mean that the alternating series test is easiest and that it actually is an alternating series. Cool. I love series stuff. I remember it being absolutely mind-blowing and just like shook my world in high school, and I struggled with it a lot. I'm going to be honest, it wasn't until like a couple years later that I felt like I actually got it. Any other questions or things coming up? If not, we can like look at another just like practice problem. Got about 5 more minutes. Y'all don't have to stick around. I appreciate your enthusiasm. Y'all want to look at one more problem, kind of just for fun? Overwhelming response. Y'all don't have to stay. I'll do one. I just love this stuff. Okay, what's a good one? Let's go to It's a good one. It's the one I'm looking for. Okay. Oh, okay. Let's do 3. I know it's hard to tell. 3A, the one that's at the top of that last page. Let's do 3A. 3A. See what it tells us. I'm gonna be pretty quick at it because I do have a meeting with College Board people at 5:30. Double check it's at 5:30. Skinny looking calendar now. Yes. Okay. All right. Real quick, let's do this. We're given this series. They give us some details about it. I'm not going to worry too much. It says it's a Maclaurin series given by this thing. We don't really care right now what that means. It's just a series. We know it converges. We know it converges on some interval. It converges on the absolute value of x is less than r. R is that radius of convergence for the Maclaurin series that we've talked about before. Use the ratio test to find r. Cool. I say go for it. I'm going to work it out here too. I'm going to talk through it, but try to do it on your own as we go. Oh, we want to use the ratio test to find r. All right. I actually don't even like to do the original fraction. I like to, if I have like a quotient like this anyways, just go ahead and do the multiply by the reciprocal thing. This helps like make my life easier. I have to write 4 steps. Right, that's what I'm looking at. Some things will cancel out. Interesting, x to the n, but I'll leave you with a x to the 1. We'll cancel out the x to the n. Not a whole lot of other stuff cancels. Interesting. So I'm going to write down my next step, keep my thoughts organized. So what I have left up here, I have n plus 1. It couldn't cancel with anything. Times 2n squared plus 1. Over the denominator of my first part would be 2 squared plus 1 times n. Notice I put brackets around this part because it's multiplying times n. Ooh, we got lots of n's and stuff. Oh, I forgot one thing, didn't I? There's an x to the first power that survived in the numerator. X to the first power, so it's just x there. Almost lost them. X to the n, can't solve with x to the n, but left x to the first power. We have lots of n stuff going on there. So what does this give us? Limit as n approaches infinity of, I know I need a limit in the end here, so all I really care about is what the biggest power of n is going to be, right? All I care about is what the degree of the top and bottom is going to be. So this, I'd have n times 2n squared. If I kind of fake this, you'd have 2n cubed, right? Times other stuff. But the degree, the leading term is going to be 2n cubed times x over, what's going to go on down here? I have an n squared, 2n squared times another n. That'll give me a 2n cubed. If I kind of 2 times n squared times n. I'm forgetting all the other junk because it's not going to give me the leading term here. 2n squared times another n, 2n cubed. Get the leading term down there. Oh, look, 2n cubed over 2n cubed. So this gives me the absolute value of x, right? The absolute value of x is really all that survived out of all of that. Kind of interesting. And the absolute value of x, all that survives. So what does that mean? Oh, we did the ratio test, so we know that that limit we just found has to be less than 1. So the radius of convergence, r, is 1. Radius of convergence is 1. When you get down here, you can see really quickly what that radius is. It's whatever that number is there. When you have absolute value of x is less than r, that r is the radius of convergence. Thoughts or questions about that one? I do have to head out, but I have one more ask since y'all are here. 2 things, if you could type them in the chat box real quick. 1, I'm debating opening up like on like Saturday or on like weekends to work on like do stuff like this, work on BC stuff and ask questions. A, would that be useful? Would you be interested in that? And B, having seen today, can you give me like, let's say a 0 would be that I stayed about where I was. A 1 would be like I feel like I am better prepared in this topic. A -1 would be like I'm less prepared in this topic and more. Can you do that for me? A, are you interested in any Saturday open times that people have questions? And B, are you got a -1, 0, or +1 for your net learning for today? A yes and a +1. Nina's a yes and a +1. I know that this is not the optimal way to learn, but y'all are troopers. I'm immensely indebted to you as your teacher. Y'all are incredible. Claire, yes, and +1. Alvin, it would be useful. Okay, cool. So I'll probably go ahead and do that. Have a great afternoon. Be sure you do help on or like answers and stuff for that tomorrow. Let me know what other things I can help out with, and I'll let y'all what I learned at this AP meeting. Bye, everyone.
Bye, Mr. McWalter. Thank you.
Bye, Alvin. Bye, Nina. Bye, Claire.
Bye, Mark Water.
Bye.